Assalamu alaikum. For control systems, we have talked about their transient specifications, we have talked about stability, and we have also talked about steady state errors. We learned that both the transient specifications and stability of a system, these are determined by location of poles of the system. So it means that if we can somehow change the location of poles of a system, then we can change these properties. To elaborate this point, let's take one particular system. We have this system. So we have this system where k is a tunable parameter. We can change k, and you remember from our previous discussion that to talk about transient specifications and stability, we always first obtain a closed loop transfer function, which is given by, for this particular system, this closed loop transfer function is obtained by utilizing the same expression, that is the forward transfer function divided by 1 plus forward transfer function into the transfer function in the feedback path. The poles of this system are roots of the denominator polynomial, and we can see that by changing this gain k, the location of the poles can be changed. We just tabulate a few numerical values of k and then gain corresponding to those, the poles corresponding to those gains. For gain equal to 0, that is for k equal to 0, the roots of this denominator polynomial, there are two roots, and that is s plus 10. One pole is at s equal to 0 and the second pole is at s equal to minus 10. So we have two poles, one pole at minus 10 and another pole at s equal to 0. If we change the gain, for example, we set gain equal to 5, then the polynomial, denominator polynomial, becomes this one, and the roots of this polynomial can be easily determined. Those roots are at s equal to minus 9.47, and the second pole is at minus 0.53. Similarly, for k equal to 10, the location of the poles is at minus 8.87 and minus 1.13. For k equal to 20, we have minus 7.24 and minus 2.76. K equal to 25, one pole is at minus 5, the second one is also at minus 5. For k equal to 25, we have this polynomial 10s plus 25, which can be factorized into this form. That is, both the poles are at s equal to minus 5. If we further increase the gain, let's make it 30, then the roots of this polynomial become complex, and these roots are at minus 5 plus j 2.24. Similarly, for k equal to 35, we have, that is, by changing this gain k over here, we can change the location of closed loop poles for a particular system. We can show this variation in S-plane, graph in S-plane, that is, here we have S-plane, which is a complex plane with real axis and imaginary axis. For k equal to 0, one pole of this system is at origin, the second pole is at s equal to minus 10. As we increase again, the location of the poles changes. For k equal to 5, one pole is at minus 9.47 and the second pole is at this location, minus 0.53. Similarly, for other values of gain, we have the closed loop poles at these locations. For location of poles for different values of gain. For k equal to 25, both the poles are at s equal to -5. If you further increase this gain k, the poles become complex, and let's say k equal to 30, we have one pole at -5 plus j 2.24, so -5 plus j 2.24, and its complex conjugate. The poles are at this location. If you further increase k equal to 35, poles are here, and further increase. So what we see is that as we change gain k, the location of closed loop poles is changed, and the path followed by the closed loop poles due to variation in this gain k is called root locus. That is, if we increase the gain k, this is the path followed by the closed loop poles, and this path is called root locus. So this root locus gives us abundant of information, that is, what is the transient characteristics corresponding to different values of gain k, what is the stability of the system for different values of gain k. However, sketching the root locus by this approach is quite tedious. That is, you have to make a big table for different values of gain k, determine the roots of the polynomial. That is quite tedious. We shall learn we shall learn an approach that will help us to quickly sketch a root locus for a given system. To explain it, to understand it, let's consider a general system given by this block diagram. Now we are considering a general system with the forward transfer function g of s and a transfer function in the field path h of s. The closed loop transfer function is given by, so where are the closed loop poles? Closed loop poles, you remember, are the roots of the denominator polynomial. That is, all the values of s which satisfy this equation are the poles of the system, poles of closed loop system. So any value of s which satisfies this equation is a closed loop pole. The same equation can also be written in this form. If I bring 1 to the right hand side, so k g of s into h of s is equal to -1. This left hand, here s, the argument s is a complex number, so this left hand side is a complex number, so you have a complex equation. And you remember that for complex equation you can always write it into this form, that is magnitude of. So this equation can be broken down into these two equations, that is, the magnitude of this is equal to 1, and what is angle of this complex number? Angle of complex number is pi. R. Pi, what is angle pi? The angle here is pi. This angle is also minus pi, so we can also write it plus pi or minus pi. This angle is also pi plus 2 pi. That is 2 pi and then another rotation. So in general, this angle is plus minus pi into 2l plus 1, where l is an integer. L is either 0, 1, 2 and so on. Thus, any point in S-plane which satisfies this equation is the same as this equation, and this equation is the same as these two equations. So any point in S-plane which satisfies these two equations will be a closed loop pole. You can see that k is a variable gain, you can always satisfy this equation by selecting different values of gain k. So therefore what we have to do is we have to check only this equation. So any point in S plane which satisfies this equation will lie on the root locus, will be a closed loop pole for some value of gain k. So to elaborate this point, let's take some particular example, rather the same example that we discussed in the previous case. We have this system. So we want to check whether this point in S plane is a closed loop pole. What we need to do is that we need to check this condition. This condition is also called angle condition. This is called magnitude condition. So let's check it for this particular system. So what is angle of this complex number? So we have substituted this value of S into this equation. We get this one. This is a negative number, and angle of a negative number is pi. That is, this equation is satisfied, hence this point is a closed loop pole. For what value of gain? We can determine it from this magnitude condition, that is k at the magnitude of this expression at S equal to minus 9.47, that is equal to 1, from where we can see that k over. So thus for k equal to 5, this is the closed loop pole. This is what we can also see from the table that we have constructed. To summarize the discussion, root locus is the path followed by closed loop poles as we change gain k. However, general approach is to construct the root locus is not the same that we discussed earlier. That is, we are not required to construct the table. Rather, from this closed loop transfer function, we can see that any point in S plane which satisfies this equation, or alternately this equation, or alternately these two equations, will be a closed loop pole. So this equation can always be satisfied because k is a variable gain, and we only need to check this equation to determine whether a point in S plane is a closed loop pole or not, or whether it lies on the root locus or not. We further explain it with another example. So we have this system. For this particular system, the open loop poles can be easily seen. The open loop poles, one open loop pole is at S equal to 0, another open loop pole is at S equal to minus 1, and another pole is at S equal to minus 2. This is the S plane with real axis and imaginary axis. Now by utilizing the angle condition, which is this condition, g of S into h of S is equal to now by applying this angle condition, we want to test which points in S plane are part of root locus, that is, which point in S plane can be closed loop poles for different values of gain. So let's take a test point over here, for example this point S1, and let's check whether this point lies on the root locus or not, that is, whether this point can be a closed loop pole or not. So for this particular system, we have remember that this k is some positive constant, so it does not contribute anything to the angle, so we just omit k in the angle condition. So we determine the angle of this complex number for S equal to S1, that is angle of this complex number. You also know that when these are multiplied, factors are multiplied, their angles will be added. So we can split this equation into this form, that is angle of 1 over S1 plus angle of 1 over S1 plus 2 S1 plus 1 here. Here is also 1. And here is 2. Which is the same as if I invert it, then angle will become negative. So minus angle of S1 minus angle of S1 plus 1 minus angle of S1 plus 2. So what is the angle of this S1? S1 is over here, this vector. So what is the angle of this complex number? The angle is equal to 180 degrees. So this is minus 180 degrees. What about this one? S1 plus 1. Is it a positive number or a negative number? So S1 is smaller than, in magnitude, smaller than 1. So this will come out to be a positive number. That is, S1 plus 1 is a positive number. So its angle of a positive number is 0. So what about this? S1 plus 2. So S1 is a number which is smaller than 1 in magnitude because it lies between 0 and 1. So again, this is also a positive number, and angle of a positive number is 0. That is, total angle is minus 180 degrees. So what about this condition, angle condition? Is it satisfied? Yes, this condition is satisfied. If L is equal to 0, we have plus 180 degrees or minus 180 degrees, whichever is the case. So this condition is satisfied for this test point. So therefore, for this particular system, this test point lies on the root locus. That is, it is a part of root locus. So this test point was taken as a general point. It can be any point from here to here. So all these points from here to here satisfy the angle condition. Therefore, this part of the real axis lies on the root locus. Let's take another test point and check whether that is also part of root locus or not. So let's take this point S2, and we want to determine whether this point S2 lies on the root locus or not. For that purpose, we shall again check this angle condition. That is, substitute here S2. So we just make substitution in the same So what do you think about this test point S2? This point S2 is a negative number. So what is angle of this negative number? Minus 180 degrees or plus 180 degrees, whatever you write. This number S2 plus 1, S2 is larger in magnitude from minus 1. So S2 plus 1 will be a negative number, and the angles of negative number is 180 degrees. What about this point S2 plus 2? This point is between minus 1 and minus 2. So S2 is less than this 2 in magnitude. So this number will come out to be a positive number. Angle of positive number is 0. So this angle is minus 360 degrees. Let's see whether this angle condition is satisfied or not. We can see that this angle condition is not satisfied for this test point. This angle can be either plus minus 180 degrees, or for L equal to 1, it is 180 degrees multiplied by 3. So this angle condition is not satisfied. Hence, this test point does not lie on the root locus. Therefore, this part of the real axis is not a part of the root locus. We take another test point S3, which lies beyond this point minus 2, and again check all these conditions. So what you will observe is that here we have S3, S3, S3. S3 is a negative number, so its angle is minus 180 degrees. S3 plus 1, S3 is larger in magnitude than 1, so S3 plus 1, this is a negative number, and angle of the negative number is 180 degrees. S3 plus 2, so S3 is even larger than 2 in magnitude, so S3 plus 2 is also a negative number, and its angle is 180 degrees. And the total angle is minus 180 degrees multiplied by 3. So this angle condition is satisfied for this test point. So this test point lies on the root locus. That is, this test point was taken quite general. So this test point can be anything which is larger in magnitude than minus 2. That is, all these points lie on the root locus. From this example, we have one hint, and that we state in the form of a rule, and we shall not always apply this approach. We shall not follow this approach to sketch the root locus. Rather, we shall apply this rule which we are going to write right now to determine whether some particular part of real axis is part of root locus or not. So I write the rule over here, which comes from, of course, this angle condition. So from this example, we have one rule which states that the part of the root locus to the right of which there is odd number of poles or zeros, that will be part of root locus. Remember that this is not the complete root locus, this is only a part of root locus, and instead of checking the angle condition each time, we shall apply this real axis rule to construct the root locus. For example, if we have this system with this transfer function given by, let's say, g of s equal to the same transfer function that we discussed earlier, and now without any computations we can just locate the open loop poles. One open loop pole is at s equal to 0, another pole is at s equal to minus 10, and we shall apply this real axis rule, which states that the part of the real axis for which there is odd number of poles to the right of it, that will be part of root locus. That is, this part of the real axis is part of the root locus. This is not the complete root locus, however, it is only a part of the root locus. Let's take a few complex systems and sketch their root locus by application of this real axis rule. We have this closed loop system, and we want to apply this real axis rule to determine which part of the real axis is part of root locus for this particular system. For that purpose, we first locate the open loop poles and zeros of the system. One pole is at s equal to minus 1, another pole is at s equal to minus 2. There is a 0 at s equal to minus 3 and another 0 at s equal to minus 4. This is the complex plane with real axis and imaginary axis. So we apply this real axis rule. So are these points part of root locus? No, because to the right of these points there is 0 number of poles and zeros. So 0 is generally considered as even. So there is this part of the real axis is not part of root locus. What about these points? To the right of all these points there is one pole. So 1 is an odd. So odd number of poles means this is part of root locus. What about this part? To the right of all these points there are 2 poles. So 2 is an even number. So this is therefore not part of root locus. What about these points? So for these points there are 3 poles and zeros. We also count zeros. So 1, 2 and 3. So 3 is odd. So this is part of root locus. What about all these points to the right of them? There are 4 poles and zeros. So these points are not part of root locus. Again, remember that this is not complete root locus. This is only part of root locus. In the next lecture, we shall learn a few more rules which will help us to sketch the root locus for a given system.